Lesson 16, Electromagnetic Radiation. Part 1, EMR. Electromagnetic radiation comes in the form of waves that carry energy in the form of electric and magnetic fields through space. Electromagnetic radiation is often shortened to EMR or EM waves, standing for electromagnetic waves. EM waves are produced when a charged particle is accelerated. Recall from our study of magnetism that moving electric fields produce magnetic fields. This was the discovery by Ørsted, and it leads to the motor effect. We also learned that moving magnetic fields produce electric fields. This was the discovery by Faraday, and it leads to the generator effect. So when a charge is accelerated, it results in accelerating electric field. And an accelerating electric field is a moving electric field, and this produces an accelerating magnetic field. But since this magnetic field is also moving, it's accelerated. Faraday says that an accelerating magnetic field produces an electric field. So this produces an accelerating electric field, which in turn produces another accelerating magnetic field. And these electric and magnetic fields continue to produce new electric and magnetic fields and travel through space, propagating as an electromagnetic wave. Electromagnetic waves are transverse waves, made up of perpendicular electric and magnetic fields. They look something like this. As they move through space, the electric and magnetic fields continue to produce each other as the wave propagates. They are at right angles to each other because of the hand rules, which show that whenever a current moves, the magnetic field produced ends up being 90 degrees to that charge. Transverse means the amplitude of the wave is perpendicular to the direction of the wave's velocity. A transverse wave looks something like this. It would travel through space in this direction, but the particle motion is up and down, perpendicular to the velocity. This particle motion is called the wave's amplitude. So if this is a transverse wave, the velocity of the wave is perpendicular to the amplitude of the wave, which is how much the wave goes up and down. The wavelength of a transverse wave is the distance from peak to peak. So the wavelength of this wave is from the peak to the next peak. And this is called wavelength. It is in fact the distance between any two repeating points. For example, here to here is also one wavelength, and same with the distance from bottom or trough to trough. Wavelength is given the symbol lambda, which is a Greek letter looking sort of like an upside down fork with only two spokes. The unit of wavelength is the meter. The frequency of wave is how many wavelengths pass in a second. The symbol used for frequency is small letter f, and its unit is the hertz. Recall from Physics 20, period is the inverse of wavelength. It's how many seconds it takes for one wavelength to pass. Period is given by capital T, and it equals 1 over the frequency. The wave equation gives us the velocity of a wave. The velocity of a wave is equal to f, the frequency, times the wavelength. The velocity of the wave is how quickly it travels through space, and that's given by the symbol v. F is frequency, and lambda is wavelength. In the case of light, we use the speed of light for the velocity. It's given by the symbol c, and c is equal to 3 times 10 to the 8 meters per second. So we have c equals f lambda, where c is the speed of light, which is 3 times 10 to the 8 meters per second. Example. Red light has a wavelength of 750 nanometers. What is the frequency of red light? So we have a wavelength equal to 750 nanometers. Nano is 10 to the minus 9. So this is 750 times 10 to the minus 9 meters. The speed of light is 3 times 10 to the 8 meters per second, and we're looking for the frequency of red light. Using the wave equation, we have c equals f lambda, so f equals c over lambda, which is 3 times 10 to the 8 divided by 750 times 10 to the minus 9. So the frequency of red light is 4 times 10 to the 14 hertz. Part 2. The electromagnetic spectrum. The electromagnetic spectrum is the full range of all possible frequencies of EMR. Visible light is just a tiny part of the electromagnetic spectrum. The rainbow of colors that we can see is found in the middle, with wavelengths ranging from 750 nanometers to 400 nanometers. So this is the electromagnetic spectrum. On the far side, we have radio waves. And next to radio waves are microwaves. And next is infrared radiation. These three are all examples of EMR with low frequency, low amounts of energy, and long wavelengths. On the other side of the visible light spectrum, we start with ultraviolet. Next to ultraviolet are X-rays, and on the far end of the electromagnetic spectrum, we have gamma radiation. On this side, all the wavelengths are short, and the radiation has high frequency and high amounts of energy. We'll start our exploration of the electromagnetic spectrum with a discussion of radio waves. Radio waves have wavelengths from 10 to the 4 to 10 to the minus 2 meters. They have long wavelengths, low frequency, and low energy. They're produced by oscillating electrons in circuits such as antennas. They're used for long-distance communication. So when you're talking through walkie-talkies, you're using your car radio, or even television signals are sent through radio waves. Radio waves are produced when electrons oscillate an antenna at the source of the wave. They travel through space with quite long wavelengths, and they hit the antenna in the receiving source. This causes smaller oscillations of electrons in the receiver at the frequency of the radio waves produced in the transmitter. Next are microwaves. Microwaves have wavelength from 10 to the minus 1 to 10 to the minus 4 meters. They have long wavelengths, low frequency, and low energy. And they're produced by oscillating electrons in special tubes and solid-state devices. There's a number of uses for microwaves. Short-distance communication, for example. All cell phones transmit using microwaves. You can also use a particular frequency of microwave for cooking food. With a frequency of 2.45 gigahertz, water molecules will vibrate, and this can be used for cooking food. There's some problems with microwaves, and you have to be careful. There may be some kinds of cancers linked to exposure to microwaves. And frequencies around 2.45 gigahertz, which is a microwave oven frequency, can burn tissue because it causes water molecules to vibrate. Infrared radiation has a wavelength from 10 to the minus 2 meters to 750 nanometers. It's long wavelength, low frequency, and low energy radiation. It's produced when electrons in valence shells transition from one energy level to another. So it's produced in atoms in the substance itself. Infrared radiation causes objects absorbing it to become warm. When you're standing around a fire and you're feeling its heat, what you're feeling is the absorption of the infrared radiation from the fire. It's also used in night vision and remote sensing. Since warm objects tend to give off infrared radiation, if you detect it, there must be a warm object nearby. The problem with infrared radiation is that it can burn tissue because hot objects give off infrared radiation which can be absorbed by tissues and skins. Next is visible light. Visible light has wavelength from 450 to 750 nanometers. You will have to memorize the wavelengths for visible light, including which wavelengths correspond to which color. The wavelength, frequency, and energy for visible light are all right in the middle, with medium frequency, medium wavelength, and medium amount of energy. It's produced also, like infrared radiation, by electrons in valence shells of atoms transitioning from one energy level to another. Perhaps in earlier grades you learned Roy G. Biv: red, orange, yellow, green, blue, violet. You need to memorize the following wavelengths for each color. 620 to 750 nanometers is red light. 590 to 620 nanometers is orange. 570 to 590 nanometers is yellow. 495 to 570 nanometers is green. Blue is 450 to 495 nanometers, and violet is 400 to 450 nanometers. On the red end of the spectrum, we have lower energy light, and on the blue and violet end of the spectrum, we have higher energy light. Ultraviolet light is next. Ultraviolet light is from just outside the color violet, which means that it's 400 nanometers to 10 to the minus 9 meters. Ultraviolet light has higher frequency, shorter wavelengths, and higher energy than the wavelengths previous. It's produced also by transitions of electrons in valence shells, but in this case, it's higher energy transitions. It's used to cause things to glow or fluorescence. It can be used for tanning in humans, and it can be used to kill bacteria. Problem with ultraviolet light is that it can cause sunburns if too much exposure, mutations if exposure over the long term, and skin cancer. X-rays have wavelengths from 10 to the minus 9 to 10 to the minus 12 meters. They're very high frequency, very short wavelength, and very high energy form of radiation. They're produced by rapidly accelerating and decelerating electrons. If you take an electron that's traveling very, very fast and smash it into a wall so it rapidly decelerates, it will give off an X-ray. They're used for medical imaging, like getting an X-ray to check out broken bones, since X-rays can penetrate most tissue, but not denser objects like bones. They also destroy carcinogenic or mutant cells. Problems with X-rays are that they can cause mutations and cancer. So you don't want prolonged exposure to X-rays. Gamma radiation is last. It is a wavelength from 10 to the minus 11 to 10 to the minus 16 meters. It's extremely high frequency, extremely short wavelength, and extremely high energy radiation. Produced by rapidly accelerating and decelerating electrons, just like X-rays, but in this case, in nuclear reactions, so very high energy electrons. Gamma radiation penetrates matter very, very deeply. It can be used to destroy carcinogenic or mutant cells on a local scale, or used to probe the structure of matter itself. Gamma radiation exposure is extremely problematic. Gamma radiation can cause mutations in cancer, radiation sickness, and even death. And unfortunately, it probably won't turn you into the Hulk or any other superhero. In summary, radio waves have very long wavelengths, long like a soccer field or a house. Microwaves are longer wavelengths as well, long like the width of a baseball or the width of a dot on a page. Infrared radiation is the width of about a cell or a bacteria. Ultraviolet is more like a protein molecule or the width of a virus. X-rays get very, very small, about the width of a water molecule. And gamma rays are extremely short wavelengths and have very high penetration. That concludes our study of the electromagnetic spectrum.